Okay, we're back again. We are going to look at chapter 1.2, which is on functions. And this has some really important things in it that you're going to use all throughout the semester. So we want to pay careful attention. They're not going to seem like a big deal now, but you'll see them over and over and over again. And so we will talk about those. But first, I want to define a function. Here's the standard map you always see. Here's a set of numbers. And then here's a set of numbers. I'm dying to make a smiley face, right? A function is one where this number, through some function, maps that number to another number in this set. So these are your x's, for example, and these are your y's. Every point on the x maps to only one point on the y. If something goes here and it maps to here and it also maps to here, then this is not a function. It's, I don't know what it is. It's not a function. And it is not useful because we want things that are a direct map between one set of numbers to another set of numbers. And the only way that can happen is if there is a direct mapping from one number to another. Okay? So that's very important. Now, it is a beautiful picture, but we are going to get rid of it. So this is called a one-to-one mapping. And that's what makes something a function. And the way you can tell that it's a function is if you have something, let's say we got a function like this. For every value of x, is there only one value of y? Yeah. And the way you test it is you do what's called the vertical line test. And the vertical line test is, can you draw a vertical line anywhere and only hit the curve once? So this x value only corresponds to that y value is what it means. And if you can draw a vertical line everywhere and only hit the curve for each line in one place, then that's a function, right? Over here, the vertical line only hits there. Over here, the vertical line only hits there. So the vertical line test will tell us if something is a function or not. Here's an example of a function, a thing that is not a function. This could be y equals square root of x. And for square root of x, let's pick a number of 4. Y equals square root of 4. What's the answer to this? 2? Plus or minus 2. So at 4, you're going to hit up here, y is going to be equal to 2, and y is going to be equal to negative 2. So when I do the vertical line test, this fails. It hits the curve in 2 places. And that means this thing is not a function because one value of x will give us 2 values of y. So when we use it on a graph, what we will typically do is throw away the bottom. And we will say the square root of x looks like this. Okay? And we're just going to limit ourselves to what's on top there. That's going to be easier for us to handle. And now when we restrict the y values, then the vertical line test works. We only go through in one place. Now, when we talk about x and y values, all the values of x are referred to as the range. Wait, let's pause it. Okay, we're continuing. I had to check that because I always screw it up. I got it right. X is a range. The values, I got to check it again. I swear that's wrong. Oops. Okay, I'm back. And I knew I had it wrong. I always do this. I think it's wrong and I switch, and then I think it's right. No, it's wrong. So that's wrong. Wait, let me look again. So the input into the function is the domain. And the output is the range. Input is X, output is Y. So the domain is all the possible X values that you can use, and the range is all the possible Y values. So for square root of X here, the domain, that's all the possible input values, that's the X. X must be greater than or equal to 0. We can't put a negative inside there, right? And the range is going to be, well, we're going to exclude the negative values. So the range is Y greater than or equal to 0 also. It could be 0 if we plug X as 0 in here. And it could be this number, this number, this number. It keeps going up. So the domain is all the inputs, the X values going in, and the range is all the Y values coming out. So let's go through and look at domains and ranges of functions and see if we can identify places where we could have trouble. Okay, so f of x equals 2 over x. What's the domain and what's the range? So the domain, which is the inputs, which is x. If it was all real numbers, I could say x equals all real numbers. That's a symbol for real numbers. Except I can't do all real numbers. There's two things I'm not allowed to do. I'm not allowed to divide by 0, and I'm not allowed to take a square root of a negative number. These are the things I always have to watch out when I'm looking at what values are acceptable. Or where does the function not work? Something like that. So for this function, I would say the domain is all real numbers, x not equal to 0. And the range is going to be, well, it could be anything. The range is going to be, so that's the domain. The range would be y equal to real numbers. You could have really big numbers. You could have really small numbers. If you put a little tiny number down here, then the fraction comes out big. If you put a really big number, the fraction comes out small. Could be positive, could be negative. So it's all real numbers. Okay? Now, if I wanted to show a graph of this, if I forget this restriction and I just want to graph the whole thing, see what it looks like. You could do this on something like, I like graphing on, let's do that. Let's go to Symbol Lab. I enjoy Symbol Lab. And can I move this thing? Yeah, I can move that thing. And I go to Graphing Calculator. And I think I have to, I think I'm sharing. Oops. I want to stop sharing, and I really want to share my desktop. What happened? I don't want that. Share my desktop. Okay, there we go. So here's Symbol Lab. Wait, I don't know that I guess I got it. So I'm going to put in here, I clicked on graphing up here, and I'm going to put in my function, y equals 2 over x. And boop, there it is. It graphed it. And I can zoom in up here. Let me move my face, goodbye face. I could zoom in if I want to see it closer. I could zoom out. I think this lets me look at points on it. Oh, this just shows the function. But you notice as x gets really big, or I'm sorry, as x gets small, this thing gets really big. Because if I make a table of values here, x, f of x, if I put in 1 for x, 2 over 1 is 2. If I put in 0.5 for x, 2 over 0.5, well, that's going to be 4. If I put in 0.1 for x, 2 over 0.1 is going to give me 20. 0.01 for x, it's going to give me 200. 0.001, it's going to give me 2,000. As this gets closer to 0, this gets bigger and bigger and bigger, until when we actually put a 0 in here. Mathematicians frequently don't like putting a 0 in. Physicists like me, I don't mind a 0 in the denominator, because I can do the math and show the limits and show when I put a really, 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 really small number close to 0, this thing starts looking like infinity. And so 2 over 0 to a physicist, we like that. We say that's infinity. This is the thing that's undefined. A mathematician might say 2 over 0 is undefined. A physicist, we like working with 2 over 0 because that's useful to us. So when you put 0 into here, the function spikes up to infinity. And you can see that here. When we get to 0, our function, let's zoom out some to see where it goes. Well, it just keeps going and going and going. It just shoots all the way up to infinity, because that's what happens when you divide by 0. And the same thing if you're on the negative side and you're slowly approaching 0, your x is getting smaller and smaller and smaller. Well, I guess you'd say bigger and bigger and bigger. It's getting closer to 0, but negative. This spikes down to negative infinity. And so this is what the graph of 1 over x looks like. And that's what we see over here when we plot this thing. We see the curve go whoop, and it goes whoop. And when it goes out here, when I put a really big number in for x, 2 over a million, that's 0.12345 It's pretty close to 0. If I put in 2 over a billion, then that's going to be 0.123456789. It's going to be teeny tiny. If I put in 2 over a cajillion, that's the real spelling. Well, as this gets so big, this gets so close that 2 over infinity just starts looking like 0. So this curve stretches out and slowly approaches the x-axis, but it never quite gets there, because can we go out to infinity? No, we can't. Just like here, we can't reach 0 and go all the way up to infinity. So these things here, where the function kind of blows up to infinity, or here, where it slowly approaches a line but never quite reaches it, these are called asymptotes. So, and asymptotes occur when you're doing something like dividing by 0. That's very common, okay? But what we really wanted to talk about was the domain and range, and that was a really long answer that introduced things that we don't need to know now, but that's okay. So here's another one. F of x equals square root of x over x plus 3. So when I'm doing the domain, I have to remember that I can't do 1 over 0, and I can't do square root of a negative. These are my constraints. So I'm going to look at that and say I can do all real numbers. Not all real numbers, that's not right. X has to be greater than or equal to 3, to 0, right? Because we want it to be positive inside here. So x has to be greater than or equal to 0, and x cannot equal 3. That's going to be the domain. These are the spots where if we use either of these, we're stepping on the third rail there in the subway and getting electrocuted. So we don't want to do that. So these are the numbers. This is the range that we have to use. Anything outside of here, the function won't work. It'll blow up to infinity or it'll do something crazy. I don't know what. So that's how we'll figure out the domain and the range, is we look for these two things, divide by 0 or square root of a negative. So now, if we talk about increasing, decreasing, this really refers to what happens when you're going left to right. So left to right is going to tell us what happens to a function. If I have this, from left to right, I'm going to say, here's f of x and here's x, that f of x is increasing. If I have this thing, and I have that kind of function, then it's increasing until you reach the peak, then it's decreasing. And that point where we go from increasing to decreasing, this point is called a relative max, relative maxima. And likewise, if it's like this, and we go from decreasing to increasing from left to right, this is referred to as a relative min. Relative minima, that's an N. So being able to identify those on a graph is really important. Now here's the big dog. If you have a function that looks like this, well, this is a curve and something interesting happens, but it's increasing here, but then the curvature kind of changes and it's still increasing. But notice here, it's kind of, if I look at this, it's kind of concave downwards. And here, it's kind of opening upwards. And the spot where it switches from concave down, where the curve is kind of curving down, then now it's curving up again, this point is called an inflection point. Okay? Now, let's talk about symmetry. Hello, kitty. You got to get out of the way. No, don't rub on the microphone. Don't bite the microphone. Go, go. She knocked my microphone down the other day. I was not happy. Okay, so if I have this, this has a line of symmetry. It looks like the way I drew it, the line of symmetry is about here, right? I could fold it on top of itself somehow. And so let me draw a better picture. So if I do y equals x squared, it's like this. And the line of symmetry is right down the axis, and I can fold it right on top of itself. I would call this, this is referred to as an even function. So if this is f of x versus x, so let me rewrite this as f of x equals x squared. For an even function, if I take f of x, right, I got x squared. If I calculate what f of minus x is, that means wherever I see an x, I'm going to replace it with minus x. Oh, okay, it's right there. So I'll put a minus x. The minuses will cancel, and I just get x squared again. So I found that f of minus x is equal to f of x, right? Here was f of minus x. X squared is f of x. When this is true, the function is even. But if I have something like, let's use a different color, my little friend red. So if I have f of x, and I have f of x equals x cubed, that looks like and like that. Okay, I cannot fold it over and have it overlap. And here's x, and here's minus x. So if I have this point here, it's going to be some positive number. If I go to minus x, it's going to give me some negative number, right? So if I take f of x is equal to x cubed, and I replace x with minus x, well, when I cube this, I'll get x cubed. But when I do minus 1 times minus 1 times minus 1, the negative sign survives. So what I ended up with, this is my original function f of x. So if f of minus x ends up equaling minus f of x, then this thing is an odd function. And we'll do some examples and show you that. Okay? So this is how we describe functions as even or odd. It's possible to be one more thing, and that is neither. That's a possible answer as well. You could be even, or you could be odd, or you could just be goofy. And that's okay. We're not going to judge the goofies, right? Okay, so let's try some examples. So we already talked of f of x squared, right? On a test, if it says, show that f of x squared, that x squared is an even function, then I would take f of minus x. Oops. Oh, well. Now let me get rid of that. F of minus x, I would plug it into f of x. Then I would square it. The minuses get canceled out. Oh, I just found that f of minus x equals x squared, which is f of x. That's even. Okay? But what if I have f of x equals x squared plus 3x? Let's try that one. So now we'll put in negative x for x. So I'll get minus x squared plus 3 times minus x. The negative signs will cancel. X squared, awesome. The negative signs will not cancel here. So I get a minus 3x. So that is not equal to f of x. So f of minus x is not equal to f of x. It's not even. Is it odd? Did I get minus f of x? Minus f of x would be minus times all of this. And if I distribute the negative sign, that would be minus x squared minus 3x. We didn't get a minus sign here. We got a plus sign here. So this is not even and it's not odd, so it's neither. Is it always neither when there's something else sitting here next to x squared? Let's see. So let's try f of x is equal to x squared plus 4. Now we put in minus x. So that would be minus x squared plus 4. The negative signs will cancel. Whoops, minus x. We found that f of minus x, well, x squared plus 4 is our original function. So if I have a constant over here, it still stays even. If there's an x over here, if you have x squared, then x to the first power, then weird things happen. So you'll notice if it's just an even exponent, you're in good shape. If I do x to the fourth plus 3x squared, I don't know, plus, let's do minus, let's do a negative number, minus 7. There you go. Now let's put in negative x minus x to the fourth plus 3 minus x squared minus 7. Even exponent, the minus sign is going to go away. Even exponent, the minus sign is going to go away. And that stays the same. This is the same as the original function. So as long as you have all even exponents, the even function is going to stay even. If you have all odd exponents, it's going to be the same. But not if you have a constant out here, because this is really times x to the 0. And here's an important thing. X to the 0 is equal to 1. Anything equal to 0, anything raised to the 0 power is equal to 1. Squiggly line raised to the 0 power is equal to 1. So notice even power, even power, even power. If I have f of x equals x cubed plus x to the first plus 1, well, this is x cubed, odd, x to the first, odd, 1 times x to the 0, even. This is going to be a neither even nor odd. That make sense? Okay. Now, let's talk about asymptotes again. You're going to have to take a function and find the asymptotes and state where they are. So f of x equals 2x squared over 4 minus x squared. Asymptotes occur when you divide by 0. Okay? So if I want to know where are the asymptotes, I first look, can I factor anything here? I can't. Okay. Then I got x in the denominator. This is going to cause something bad to happen when 4 minus x squared is equal to 0. Okay? When x is equal to plus or minus 2, we're going to get a 0 in the denominator. And as I explained before, when I get a 0 in the denominator, the function's going to explode. And it's going to go to either positive infinity or negative infinity. It depends on the problem. So we're going to have asymptotes here at x equals plus or minus 2. Now let's go back over to Symbol Lab and let's look at that. So 2x squared. So we got to do a fraction first, then 2x exponent squared over 4 minus x squared. Okay, there it is. So here's 2. So we're right here at 2, and we're over here at negative 2. And so as x approaches 2, it spikes down to negative infinity. So when it approaches 2, so we would write this, the limit as x approaches 2 from the positive side of 2x over 4 minus x squared. This is going to give us negative infinity because we're going to divide by 0, but we're going to be on the negative side here. Okay? So think about this as if x was equal to 3. 4 minus 3 squared is 9. 4 minus 9, that's a negative number. So at 3, we're down here at a negative number. When we're in between the plus 2 and minus 2, this function is positive. Because if we're at 1, 4 minus 1 squared, 4 minus 1 is 3. Oh, that's positive. So we're going to be in between here. And then over here, outside of negative 2, again, we spike down to negative infinity over here. spike up the plus infinity inside. Okay, so I could write it limit as x approaches 2 from the negative side. So that means you're approaching this way. Oh, 2x over 4 minus x squared. That's going to equal plus infinity. So this is how we write it. This is how we show we approach from the positive side, we approach from the negative side. But all we want to do right now is identify where are these asymptotes. And the asymptotes occur when you get a 0 in the denominator. Okay? That's always going to be the case. Let's see, where are we here? Oops, I got to turn that off. There we go. Nope. Nope. I want to be there. So finding asymptotes, very important, not terribly difficult to do, but oops, I'll do that. But you got to be good at it. Hello, oh, that's from Cami, or from, there we go, Zoom. Okay, so here's another function. So 3x over x squared plus 1. Are there any vertical asymptotes? Can we divide by 0? There's no way we can make the bottom 0 because x squared will always be positive. But can we make, are there any, if we ask for the end behavior, meaning if you go back and look at this, notice that when x gets really big, this thing starts settling down to a number, looks like -1, -2. So this has an end behavior of when x gets really, really big, the function becomes -2. And when x gets really, really negative, x becomes -2 as well. So this is referred to as the end behavior. And it's also referred to as when you have a function, and maybe you have a function that does this, and it settles down and approaches some number but never reaches it. When you approach some number but never reach it, that's referred to as a horizontal, O-N-T-A-L, asymptote. And that's what these things were. No, where'd you go? I don't want that. Go away. No, go away. There we go. This is referred to as a horizontal asymptote, and you can even see that Symbol Lab even tells us that's a horizontal asymptote, and this one's a vertical asymptote. So the end behavior, yes, I will use your cookies. The end behavior is what happens if it settles down to something like this. It's a horizontal asymptote. And the way we figure it out is end behavior happens when we put a really, really big number in here for x, like infinity. But it's hard to plug infinity into things to find horizontal asymptotes. So to find a horizontal asymptote, there's a process and there's steps. Step 1, divide by the biggest power of x. So you divide everything by the biggest power of x. So I'm going to take this, biggest power of x is x squared. So I'm going to write it as 3x over x squared over x squared over x squared plus 1 over x squared. Okay? Step 2. Simplify and cancel wherever possible. Okay? So let me get rid of my nice little curve. So let's simplify. So I can write the numerator 3x over x squared, that's going to be 3 over x. All over x squared is 1 plus 1 over x squared. Step 3. Plug in infinity. Plug in a big honking number. So over here to my function, if I get 0 over 0, then I don't have a limit. Something funny happens. But let's see what we get here. When I plug infinity into here, what's 3 over a really, really big number going to be equal to? 3 over infinity. Right. Anytime you divide by infinity, that's going to give us a 0. Because you're dividing 3 by 100 gajillion. And 3 over 100 gajillion is really freaking close to 0. So when you use infinity, we're going to call it 0. Over 1 plus, what's 1 over x squared? 1 over infinity squared. Let's see, 1 over cajillion squared, that's 1 over something really, really big. That's going to give us something really, really small, which is approximately equal to 0. So 1 over infinity squared is going to be 0. So we end up with 0 over 1, which is a number, and we like that. Here's the horizontal asymptote for this thing. As x gets really, really big, it's going to slowly approach 0. And we did it, let's see, we approached infinity. We assumed it was positive because we used positive infinity. What if we use negative infinity? So we have 3 over negative infinity over, that's still going to be a 1, plus 1 over negative infinity squared. The negative's just going to cancel. So this is still going to be 0. It's negative, but it's still going to be 0. And this is 1 plus 0, so I think we're going to get the same thing. So let's plug this one in. 3x over x squared plus 1. So I got to make a fraction first. And then, oops, 3x, go down there, over x squared, got to have an exponent. Make sure you're not in the exponent when you do the next part, plus 1. There it is. So when we're on the positive side, we approach 0 from the positive side. When we're down here in the negative, we also approach 0. So we get closer and closer to 0 and never touch. We can zoom in and see if there's anything, oops, can't do it that way, sorry. We could zoom in this way, see if there's anything interesting happening in the middle, and there's nothing. So this function, its end behavior, is it has a horizontal asymptote at 0. Oh, look at that, it even says horizontal asymptote. Wow, Symbol Lab is smart. So this is how we calculate how functions behave, where their asymptotes are. Very important to find their asymptotes.